Communication technology is always improving. Different methods of sending and encoding information have been developed to address the problems of mobile digital communications. One such method is orthogonal frequency division multiplexing, or OFDM. This is our senior design project. We are Blackbird 19 of EE488 Communication System Design. I'm Gabriel Jordan.
I'm David Bourne.
I'm Connor Hearn.
I'm Patrick Nguyen.
And one of our members, Chengyu Zhu, couldn't make it here today. This is our senior design project, OFDM. What makes OFDM special? It was developed to address the problem of multipath fading. Multipath fading is when signals reach a receiver via paths of various lengths. Signals can interfere with one another and be reflected by physical obstructions, such as buildings. The receiver can also be moving, thus not creating a direct path between the transmitter and the receiver. These interferences cause distortion, delays, and degradation of network performance. The defining features of OFDM include parallel transmission and orthogonality. Parallel transmission takes one channel of high-speed data into several parallel subchannels. This allows for faster data transmission. Orthogonality means each signal, with its own frequency, is statistically independent of each other. This allows signals to overlap without distortion, allowing more information in a single frequency bandwidth. Our objective is to recreate the OFDM system in MATLAB based on this block diagram and compare the output data from the input. Each of the group members will explain their assigned parts. We will start with the transmitter. Our input information data will be this image of Sonic the Hedgehog. The image will be processed, transformed into a parallel matrix, and then modulated based on 16 QAM. The image was converted from a string matrix of decimals to binary code in serial form. The serial code was reshaped into a parallel matrix. The modulation scheme most often used in OFDM is quadrature amplitude modulation, or QAM. 16 QAM means there are 16 groups of 4 bits. Here's the 16 QAM constellation. This plot shows values in the complex plane that are used to specify certain bits. For example, 1 plus 1j is applied to 0, 0, 0, 0. Matrix indexing was used to modulate the information all at once. The parallel bit information is converted to decimal form, then summed together in every row, creating values from 0 to 15. In a small for loop, the decimal matrix is compared to values n-1, with n equaling 1 to 16. If the comparison is true, then the nth symbol is multiplied by 1 and added to a matrix of zeros with the same number of parallel subchannels.
Our inverse fast Fourier transform, known as the IFFT, uses a mathematical trick that allows the FFT, or the fast Fourier transform, to perform the IFFT. To summarize, the IFFT process consists of taking the input data and performing a complex conjugate, then the FFT function, and then taking the complex conjugate again. The result is then divided by the number of input data points.
The purpose of the cyclic prefix is to eliminate inter symbol and inter carrier interference by copying the end of a symbol and pasting it to the front. Carriers can be delayed, causing the system to lose orthogonality, but it is restored by converting the linear convolution of this channel to circular convolution. For the cyclic prefix to function correctly, the length of the cyclic prefix should be longer than the channel impulse response to prevent interference.
Digital to analog conversion, or DAC, is used to change our complex signal to analog form, while analog to digital conversion, or ADC, is the opposite. DAC is used in our system to change our complex signal to analog form. To achieve this on a complex number, we need to separate the real and imaginary values and apply one DAC to each part. Since complex numbers can be represented as cosine plus j sine, the real part will be multiplied by cosine, and the imaginary part will also be multiplied by cosine, but phase shifted by pi, or 90 degrees. DAC also acts as a carrier signal, so a high carrier frequency must be used. Then, the signal will be sent to the receiver over a noise channel.
For the noise channel, we use AWGN, which is typical random noise. The user can pick a value for the signal to noise ratio, or SNR. We also experimented with Rayleigh and Riccian channels. Rayleigh and Riccian channels both simulate multipath fading, but the difference is Riccian takes into account line of sights.
And now, onto the receiver.
Analog to digital conversion is the reverse of digital to analog conversion. On the frequency spectrum, when a signal is multiplied by cosine, the input signal will shift to the positive and negative frequencies of the cosine. To get our signal back, we will again multiply the real by cosine and the imaginary by phase shifted cosine. This will bring the signal back to frequency 0 Hz, and we'll combine the real and imaginary parts together by addition to get the signal as it was before DAC. The low-pass filter passes everything within the passband frequency and filters out the rest.
The cyclic prefix is removed by taking the length of the cyclic prefix and removing it from the front of the symbol.
Our FFT function uses a known mathematical trick called the Cooley-Tukey method. In order to simplify the Fourier transform, the function first reorders the input signals into time domain singular points. This is known as the bit reversal process. The Fourier transform of a time domain singular point equals a frequency domain singular point of equal value. The resulting frequency domain singular points must then be combined into one signal. A process known as the decimation in time radix 2, commonly known as butterfly loops, combines two signals into one signal of twice the length. The butterfly loop process is then repeated with the larger signals until they are all combined into one signal.
Matrix indexing was used once again for demodulation. The FFT result was compared to the original complex values from the transmitter. If the solution is true, then the corresponding bits are applied. The image was then reassembled to match the original input. Chongyu Zhu was put in charge of the bit error rate. The number of errors was divided by the number of transmitted data points to obtain the BER. Now for some results. If the user inputted a signal-to-noise ratio of 10, there is a good amount of errors. If the SNR is 20, there are less errors. As the SNR grows, the BER essentially becomes 0%. Our project was implemented successfully. Our group learned a lot about OFDM and digital communications. There was some room to improve with the fading channels, but overall, the image was processed as it should have. And that is our video of our senior design project, OFDM. We hope you enjoyed this video, and we hope to continue learning in the field of digital communications. Take care.